Hello, and welcome to the Omniscien Technologies webinar, Introduction to Neural Machine Translation. My name is Andrew Ruffner. I'm the CEO of Omniscien Technologies, and I'm very pleased to be your host today with our esteemed presenter, Professor Philipp Koehn, who's Omniscien Technologies Chief Scientist. This webinar is designed to give you an understanding of neural machine translation, how it compares to other MT technologies, its basic inner workings, and the opportunities and the challenges that are associated with it today. This webinar is part of a series of Omniscien Technologies webinars on NMT and its applications. Before we start, I'd like to take care of some housekeeping. This presentation will take approximately 45 minutes and will be followed by a Q&A session. The presentation will also be recorded, and we will post the recording and the FAQ online a few days after this call. If during the presentation you've got any questions, please type those into the chat box on your GoToWebinar client. We will select a number of the questions for Q&A after this presentation and would like to ask you for a kind understanding that due to the larger number of questions we will most likely get, we will be unable to address all the questions during this webinar. However, we will try to answer all of your questions in an FAQ that we will post on our website following this webinar. Before we head off into the presentation, I would like to just take a few moments to quickly introduce Omniscien Technologies. Omniscien Technologies was founded in 2007 at Asia Online and was rebranded very recently, last year in Q3, as a result of an updated and broader offering that we're taking to market in a far more global clientele. Omniscien Technologies is a global supplier of specialized and highly scalable language processing, as well as machine translation and machine learning solutions. Looking at the translation solution specifically, we offer more than 546 language pairs for machine translation on the Language Studio platform, and have been named last year as the leading specialized MT solutions provider in a Slater MT Vendor Global Market Analysis. Our customers spread across different industries, sectors with primary segments including the localization industry, enterprise, e-commerce, online travel, media, online research platform providers, government, financial services, and e-discover, as well as many others around the globe. With the introduction to Omniscien done, let me introduce our speaker today. Philipp Koehn is Omniscien Technologies Chief Scientist and our presenter today. Philipp is a professor of computer science at Johns Hopkins University and holds the chair for machine translation in the School of Informatics at University of Edinburgh. Philipp is very well known as a leader in the field of machine translation research with more than 100 publications. Many of you may know the open source system Moses, which has become the de facto toolkit for machine translation and which was developed under the leadership of Philipp. As Omniscien Technology Chief Scientist, Philipp has refined machine translation technology for the use in real-world deployments and continues to drive innovation and technical developments together with us. Now, with the introduction done, please let me hand over to Philipp. Philipp, over to you.
Yeah, hello. So as we had a presentation on neural machine translation back in December that was quite popular, so we decided to give a bit of a broader view on machine translation and neural machine translation. So this is the point of this webinar. I'm actually going into quite a lot of technical details. I'll start with kind of a big picture view of the history of machine translation to give some perspective about what new developments mean and where things might be heading in the future. I'll quickly review statistical machine translation, but I will spend most of the time on technical details of neural machine translation and end up with practical guidance of where neural machine translation is right now, or machine translation in general, and we'll have time at the end for a question and answer session. So machine translation is a very old idea. This is a quote that is frequently quoted by machine translation researchers. When machine translation started out from people who worked on code breaking, they thought machine translation is just like code breaking. When I look at an article in Russian, I say, this is really written in English, but it has been coded in some strange symbols. I will now proceed to decode. So the task of translation might just be very similar to breaking a code. So there have been very early efforts in building machine translation systems. So these are the ancient days of computers. There's a famous 1954 Georgetown experiment where a machine could translate 250 words and use 6 grammar rules. So these are really old computers that have very limited capability. This line of research, which was pretty active and explored a lot of different directions, came to an end with a famed 1966 ALPAC report, which pretty much concluded there's not really much point in machine translation. There's not really that much that needs to be translated. If you spend so much money on research, it doesn't really justify the actual need for it. Following this, there were still people working on machine translation research and building systems. So we can classify generally these type of systems as rule-based systems. The idea is that you have linguists building dictionaries, writing transformation rules, and then you see how it works, and then if there are failures, you refine the rules, build new dictionaries, and so on and so on. The general problem with that is it actually gets you started pretty quickly, but then you have a lot of interactions between all these different transformation rules, so it's really hard to scale this up massively. But there were early successes. There's a weather forecast translation system, so this is a very limited domain. So you can see that you can fully capture what needs to be translated there. Already in 1976, Systron started even in the 60s building rule-based systems, logos and metal in the 80s. So these have been the state of the art pretty much until early the 2000s. Statistical machine translation was invented, or at least the term was coined, by IBM, who built a very pioneering system, which was followed up by increased research on the topic, and in the mid-2000s it really came to life. Phrase-based variant of the original IBM ideas was developed. This is what the Moses system does, is what Google is doing. It really reached commercial viability around 2010 and has now really taken over the field and made it much, much broader applicable solution and technology. Since the mid-2010s, so really just the last 2 or 3 years, neural network models have been introduced to machine translation, and that's definitely where currently a lot of the research focus is. And we saw last year early announcements of deployments of this. Here's one lesson from history, which is there's always a discrepancy between hype and reality in the field. And machine translation researchers in general are very aware of that and very cautious of not promising too much. But with each new wave of people coming into the field and discovering it new or using their method now to this new problem that is new to them, they tend to oversell what is capable. So here's a bit of a obviously completely made up chart of what the hype is and what the reality is. And the reality is definitely that this is technology that has become practical and useful in many, many ways. For translation of web pages in a foreign languages when you travel abroad to get information about how to use the metro, or even to help translators to be more efficient in translation. But there's also an up and down in the hype. So we've actually seen before the latest neural machine translation hype a bit of a negativity about machine translation, that it doesn't really make any progress anymore and it's stalled. And now again is the big hype with promises of near human translation that I would be a bit cautious about. So where are we heading? So here's one vision. So at the simplest form, machine translation might be as simple as using a dictionary. So you take the source sentence, map it to the target sentence by just lexical transfer. A bit more sophisticated would look at syntactic structure. So if you analyze, for instance, a German sentence, we notice that often the verb is at the end and subclauses or when auxiliary verbs are used. And in English, the verb is in a different position. Japanese also has a very, very different word order from English. So just mapping words is not enough. If you would know something about syntax, you might do a much better job at translation. The next step then is to do semantic transfer, where we go just beyond just the syntactic analysis about what is the subject and the object, but to really go to the meaning of things. Grouping words together that have similar meaning, actually getting abstract meaning representation. And then ultimately the vision is to do interlingua, to have some representation of meaning that is beyond language. And that's kind of the grand vision of a lot of natural language research in a way. So this is one vision. And here's another vision, which is just saying, well, let's not worry about what language actually is. Let's just throw big computers and learning algorithms on the problem. This is a field where we have a lot of data and we can learn a lot of things automatically. So we started with these probabilistic models in the 1990s, the IBM statistical machine translation models. We've already seen, following that, increasing use of machine learning method, discriminative training, Bayesian method, Monte Carlo sampling. All these kind of things were explored in many ways, and a lot of them have actually been found use in the today's use technology. So the latest hype along this wave of trying out different machine learning methods is obviously neural networks, which started about 2 or 3 years ago, so the mid-2010s. There's always a fight, apparently, between the linguists and the machine learning researchers, what works better. For instance, we've seen a lot of really good success with syntax-based models for translating German and English, and Chinese English. The state of the art for that a few years ago was definitely statistical methods that did syntactic analysis, and that did much better than statistical methods that didn't do syntactic analysis or any other fancy machine learning algorithms. But now the wave is again towards machine learning, so the neural network methods are currently the one that dominate the field, and linguistic insight is taking a backseat. But this might change. Okay, I'll now quickly go over statistical machine translation, mainly to introduce some core concepts and kind of ground what they're going to say afterwards about neural machine translation to also make clear what the differences are. So the basic idea of a machine translation is, statistical machine translation is that to learn from data. So if you have a bunch of documents in German where the word Bank occurs frequently, you look at English documents that are translations of them, and you'll observe sometimes there's the word bank and sometimes there's the word bench. So maybe these words are translations of each other. They co-occur a lot, so probably they're translations of each other. And the word is ambiguous. It's more likely to be translated into bank than bench, but both happens. So this is roughly the kind of analysis that's been done with obtaining these models, of learning these models from the data. It's obviously a bit more sophisticated. For instance, we try to establish a word alignment of each word in the German document to each word in the English document. But we do this actually completely unsupervised, meaning we don't provide any hand annotations of word alignments. There are two major objectives when it comes to translation. And this is also well known for any student of translation. So the one is what we call in the field adequacy, and the other one is fluency. Adequacy is the idea that the translation must have the same meaning at the source. That's pretty obvious. So we need to have a model that assigns a score to a foreign sentence paired with an English sentence saying how likely are they translations of each other, how well do the words match up. So that's obviously one goal. Another goal, however, is also that the translation must be fluent in the target language. So it must be a sentence that a native speaker in the language would be saying. So we need also a model that assigns a language score to each sentence. And these two goals are to some degree in conflict. Yes, we want to have very fluent translation, but they also have to be true to the source. And if you want to be really true to the source, you're going to write something that is not very fluent in the target sentence. So this balancing depends a lot on the task at hand and what the use of the translation is. For literature, for instance, you might care more about fluency than adequacy, but if it's legal text, you care much more about adequacy than fluency. So these are then the two models that we have in statistical machine translation systems. So we have a translation model that is trained on parallel text, so English and foreign text paired with each other. We do a lot of statistical analysis on that, and we get a model similar to the one I just showed earlier. Maybe you have probabilities of words translating to other words, words being reordered, and so on. We also take a lot of text in the target language and do a statistical analysis of that and build what we call a language model. So a language model is just pretty much a model that says how likely is the following sequence of English words a fluent English sentence. With these two models in hand, we can then go ahead and take a foreign sentence and decode it into an English sentence. That's the task of a decoding algorithm. Here's in one slide the dominant solution for statistical machine translation, which is the phrase-based models. The main idea here is, beyond what I said before, is that we not only translate words individually, but we translate phrases of words. That has a lot of benefits. Often one word gets translated to multiple words. In this example, natürlich get translated into of course. You also get idiomatic expressions nicely translated. So the question, how could you possibly translate it's raining cats and dogs? Well, you just learn it as a big phrase and then map it to a phrase in the other language that has the same meaning. As long as it occurs in the data, you are able to learn any kind of idiomatic phrase, compositional phrase that is not easily explained by its constituent words. So you have these phrases, so the input is segmented into these phrases. Each phrase is mapped into the target language, and the phrases might also be, of course, reordered. And that's pretty much all it is. So when you come across a sentence you have to translate, you look up for each word and phrase to a string of subsequent words or the possible translations for them. These are obviously a lot. And now the task is, given this huge table of translation options, how do you produce a nice fluent target translation? So you start with the beginning of the sentence, nothing is translated yet, and then you pick one word in the foreign language and pick a translation for that, and that's one hypothesis. Obviously there are many choices, so this blows up quite a bit, and then you continue from there. So this looks like an exponential explosion of possible translations, and yes, that's true, and there's obviously then a lot of pruning and optimized search to find still the highest scoring translation, even given that the search space is really large. So the ultimate goal is then to find a final translation that goes all the way to the end and has the highest score according to these translation models and language models we built. So, so this is a very successful method. Here, I just want to list some disadvantages to motivate why neural machine translation currently gets attention. One is that the phrase translations do not consider context. So words have very different meaning, but if they are basically translated here in isolation, if they're not part of a phrase, but if they're part of just a single word translation, we don't care what's outside to the left or to the right of that word. And meaning can be often determined from context. That's how we understand, for instance, the difference between interest rate and interest in pictures. We just need a few more words around it to know the differences of meanings in ambiguous words. And in statistical machine translation, the only thing that really considers context beyond the phrase is the language model, which has a slightly larger window, but it only operates on the target side. Another problem is that we don't really have generalization between phrases. So the word cat and the word cats are just defined as different tokens. They all have their own translation entries, and there's no effort being made of sharing the information. So the training data for cat is not used for cats. So when I see cat in the corpus, I don't learn anything about how to translate cats. There are obviously a lot of efforts in this direction to remedy that, either by morphological analysis, which would be a good solution here, or by automatic clustering, which might be also group words together that have the same meaning. Okay, let me now go through a fairly detailed but still, I hope, gentle introduction to neural machine translation. And let's start with one task first, which is, can you predict the word in the middle of a sequence of 5 words? So we have now trying to have the words the big and then bark loudly, and can you predict the word in the middle? This is similar to a language model, that's why I'm introducing it. So can you figure out which word fits best in a context, which is ultimately the goal of a language model, which words fit together nicely in context. This is the neural network solution to this. I'll go into a little bit more detail in a second. So the basic idea here is we first have representations for these words. For these we take high-dimensional vectors where only one of the elements in the vector is set to 1, all the other ones are set to 0. We then map them to what we call embeddings. So these are the red boxes. Also a vector with lots of numbers, but now they're continuous numbers. And then these get mapped to the green box, which is the hidden state. Also a relatively high-dimensional vector with continuous numbers, and from that you cannot predict the target word. So one key piece of this puzzle here is this mapping of this one hot vector representation where only one of the elements is 1, all the other ones are 0, to an embedding. These are typically, just to give you a number, about 500 dimensional vectors with real valued numbers. So this is still a very large space. A 500 dimensional vector with real valued numbers, that's a huge space of possible values this can take. So mathematically what is happening in all these mappings is matrix multiplication followed by a nonlinear activation function. So these are vectors to map a vector to a vector. A matrix does that very nicely. Basically all possible linear combinations of the input values to output values. And the nonlinear activation function is key to avoid that what all this doing is just a linear combination. So the nonlinear activation function is actually key to make neural networks work. What you get out of it is something like this. So if you look at the embeddings and now break them down to 2 dimensions, you get these nice pictures where words that have similar meaning, like scoring, playing, winning, losing, all end up with very, very similar representations. So the main benefit here is that not only do you get synonyms kind of clustered together into the same class, you also get words that have similar meaning. So then you can learn from a word that occurs in a particular context and transfer that knowledge to a word that is basically a synonym of it, or a very closely related word. Here's some work about saying this is maybe a solution to the deep problem of semantic representation. How do you represent meaning in a computer? Maybe all you need to represent meaning is high-dimensional vectors. So here is from an influential paper that argued that these vector representations between words show patterns that allow you to, for instance, say man, woman, so the change of a gender of a word, you always have the same difference in vector representations there. And you can use then these difference in vector representations to do calculations that know the relation between king and kings, and queens, and then you also know the relation between king and queen, and you can infer other words from that. Okay, having said that, we're now hopefully somewhat prepared to go into neural machine translation. So recall that we had 2 models earlier, and you still have the same 2 models in mind. There's this language model to ensure fluent output, and the translation model to ensure that we have adequate translation, meaning that the translations have the same meaning as the source. So we basically need to have those things in neural machine translation as well. We'll start with the language model. So when people in natural language processing in general, and especially machine translation, talk about language model. They typically talk about sequential language model. So it's basically the task of, can you predict the next word? So if I have a sentence that starts with I, what is the next word? Well, for I, there might be many words that follow. I like. Well, that doesn't really help that much. There might be still many words that follow. Except, grammatically, I like to is probably a good idea. So I like to, that's a very probable next word that follows. So what's the next word that follows? Probably a verb, but we don't know which one. I like to learn. What is going to follow learn? Learn about. And now, what might be the next word? Machine. And now you're hopefully prompted enough by the general context of this talk what the next word might be, translation. So this basically is the task of a language model. So language model sounds a bit grandiose, but it's really just the task of, can you predict which words fit next to each other? And this is how they're generally formalized. Given a previous sequence of words, can you predict what the next word is? What is the most fluent word that fits in there? Okay, here's in one slide a neural language model solution for that. So we have these word representations at the beginning, we have some hidden layer in the middle, and then we try to predict an output word. That's our first idea. So this is now doing language modeling with neural networks. So we have this high-dimensional representation for the input words. We try to predict the high-dimensional representation of the output word, and we add some layers in the middle to do additional computation. And here, just to be really clear about it, when I now talk about the input word and the output word representations, I mean these one-hot vectors, where all the elements of the vector are 0 except for one of them, which corresponds to the word we actually currently have on the left side or try to predict on the right side. These neural language models are a little bit more sophisticated in that they first, before they go to that hidden layer, also have this embedding step. So this is what I introduced earlier. First, the word is mapped into these also high-dimensional vectors, but much lower dimensions than the input words. So the input words, you have a vector that might have 50,000 or 100,000 dimensions. The embedding only has 500 dimensions, except it has continuous space values. And from these embeddings, we then predict the hidden layer, and from that, the output word. So that's one idea. This is classic neural network design that has been around for 20, 30 years. I should say that a lot of actually the concepts in neural machine translation are not necessarily super novel, but what helps us nowadays is to finally have the computing resources to put them to work on a complicated task like machine translation. Okay, here's a slightly different idea how to do the whole thing. So here we try to predict one word at a time from previous words, and we don't want to be restricted to just a window of 4 previous words. So let's start at the beginning. So we have the beginning of sentence symbol at the very beginning. That's the given word. Even the beginning of sentence symbol is going to have some embedding, so we're going to map to that. From that embedding, we map to a hidden state and predict the output word. So basically, what we're predicting here, what is most likely the first word of a sentence? If you look at English language, 10% of all sentences in news start with the, so the is always a good way to start a sentence. So then when it comes to predict the next word, we take our prediction that we just made, the word the, and stick it in as input to predict the next word. So we commit to one of the words that were predicted, the most likely word, and then basically repeat this process, except now in the hidden state, we don't only care about the embedding of the current word, the, but also all the previous words. So the green box has arrows coming in both from the top, so from the just last word we just put in, and from the left, so everything that preceded it, which in this case is just beginning of sentence marker. And we basically keep doing this. So this is called the recurrent neural language model. It might not seem now that much, but this is already 80% of what neural machine translation is in a way. Okay, so this gives rise to this idea of an encoder-decoder model. So we try to predict the words in a sequence. Why not also predict their translation? So if this is a method that allows us to figure out what is a good sentence, why don't we just run this first over the input sentence and then use that to predict words in the output sentence? So basically, we're connecting up now the input sentence, the house is big, and try to predict from that an output sentence here, a German sentence, das Haus ist groß. So as we kind of hope that in these green boxes, in these hidden states, there's enough magic in there to capture the meaning of the input sentence to then produce every single word in the output sentence. So if you look at all the words in the output sentences when they're ultimately predicted, you can see errors going back to everything in the input. So everything is technically connected. So with smart machine learning, you might actually, to learn the right values for everything, to pull this off. This seems, I'm writing here, obviously madness. You expect a lot from the hidden state to pull this off. How could this possibly work for 30, 40, 50 word sentences? And the truth is it doesn't really work for long sentences. But this has been seriously proposed, for instance, by Google in 2014 as the solution to neural machine translation. Okay, what is missing from these models? Some kind of alignment of source words to target words is not really in there at all. So yes, we walk through all the words, but we're not really connecting up the source words and the target words. But it might be nice to have some kind of mechanism to map the target words back to the source words. This is the motivation for the attention mechanism. And that is really the last piece of the puzzle for the current dominant approach to neural machine translation. So here's the big picture of that. I'm using more or less the same colors as before. What you notice is that there's in the middle something called alignment and input context that connects up these output words that we produce back to the input words. Okay, this is a very complicated picture. The top part should not look too unusual because we just went over it, but the bottom part is somewhat disconnected from that. Let me walk through that a little bit more slowly. So as I said, this is currently the state of the art in machine translation, in neural machine translation. This is more or less the model that is being used currently by Google in their online system, by WIPO for their translation system. Cistern, they announced neural machine translation. This is the kind of model. This is something we're looking at Omniscien as well. So what do we have here? Well, we start with the input word embeddings. So this is the first mapping step from one hot vector to these continuous space representations that supposedly have some meaning. And then we pretty much do what you would do in a neural language model. So we walk through the sentence left to right, try to predict what the next word is, and while we're doing this, we have these green boxes here, these hidden states. And they capture pretty much the meaning of the sentence up to that point. So since this obviously has a bias towards the left, so at each point you know what happened previously to the left, but you don't know what happened to the right. We actually do it in both directions, left to right, right to left. So that gives us then, under each word, a representation that captures the left context of a word and the right context of a word. And with that in hand, we have a pretty good representation of the input sentence. We have a representation of all the words in the input sentence and how their meaning is in this particular context. So this is the right to left and left to right recurrent neural network. This is really just the language model that we just talked about earlier. So on the output, we do something similar. So we have to produce output words, and we produce these output words just like before from a hidden state. So a hidden state produces output word, and that hidden state now is, to one hand, informed by the input context. So some weighted combination of input states. This is where the alignment comes in. So we have to weigh at each point how much do we pay attention to which words in the input sentence. So maybe at the beginning of the sentence we just pay attention to the initial words, and then we kind of move forward through the sentence. Or if there's certain syntactic patterns between the input language and the output language, we might jump around quite a bit. If I translate Japanese to English, I know that I should very quickly jump to the end of the sentence because that's where the verb is, which I need in English, rather at the beginning. So this is what the alignment mechanism here does. So the input context that is in this OLED box encoded is a weighted sum of input representations of all the input words. So the benefits of this kind of model is that each output word is predicted from the encoding of the full input sentence and all previously produced output words. So yes, we'd still walk sequentially through the output words, but at each point that information, the prediction of that output word is informed by pretty much all the available context. If you're a human translator and translate a sentence, you're aware of the input sentence, you're aware of everything you've written so far. All that's going to influence what next words you choose. And this model is fully conditioned on all these various pieces of information. Since we use word embeddings, we also allow generalization. So cat and cats have similar representations. House and home have similar representations, so we can share some knowledge about them, how these words are used, and what they mean, and what they should translate to. So one of the reasons why this is now hugely popular in the research world is these kind of models have been shown to be more successful. So here's one example of a competition that we organize every year with various other universities on news translation, where various research groups participate, and we also use online systems to submit their translations to kind of calibrate how well does research stack up to currently deployed technology. And last year, so 2016, the best systems in that competition were neural systems. I like to point out here the best traditional statistical MT system is the one that uses syntax. So there might be some hope in the future of combining linguistics and machine learning to produce even better translations. Okay, let me conclude with some practical guidance, also a bit of a reality check where things are, how well things work. So the benefits of neural machine translation is there's ample evidence that you get overall better translation quality. Especially a lot of long-distance relationships seem to be handled better. The ability to take broader context to account to make word predictions allows you to produce better informed translations. It has the ability to better generalize training data, better handling of sentence level context, and also generally better fluency. The output sentences seem to be more grammatical. The traditional statistical machine translation system that have a 5-gram language model only look at 5 words in context, so overall the sentence might not be very fluent. Here we always have a view of the entire sentence, so we might produce more fluent translations. One problem is that there's actually a limited vocabulary for all these models. So if you remember this first step, we take a high-dimensional vector and map it to embedding. Well, we need for every vocabulary item 1 dimension in this vector. So I said earlier 50,000, 100,000, and these are the numbers that are being used. But if you collect a lot of data, if you have a lot of parallel text, which is currently available in hundreds of millions, if not billions of words, you get vocabulary sizes of millions of words. So that has to be addressed somehow. One standard solution to that is to break up words into subwords. So only have individual entries in this vector for frequent words, or for infrequent words you may break them up. There are even general ideas about completely do away with this idea of words and just do translation based on characters. Just break up the input in the next sequence of characters and then predict the sequence of output characters. There are also ideas of just saying we're just going to have neural MT for the frequent words and for the rare words. We fall back to dictionaries or phrase-based models. Here is, just as a reminder, part of the picture, what I had earlier about adequacy and fluency. So if you see at the right hidden state there, so the right purple box, the errors coming in from the top, from the input, and the errors coming in from the left, which are the previous output words you produce. So the error coming from the top is in a way the translation model, so yes, the next word prediction should have something to do with the input segments. And the error from the left is from the previously produced words. Yes, the output word you want to produce now should fit in with all the other words we have. It should be fluent. There seems to be some evidence occasionally neural machine translation gets taken over by the language model and produces output that is completely unrelated to the input. This seems to be especially happening a lot if you go out of domain. Here's some things someone posted on Twitter about things where one online MT system screws up if you give it somewhat degenerate input, but stuff that still should have been translated well. So knife, fork, knife gets translated to German, which basically means knife, 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 so the fork disappeared. If you give it weird input like Messer, Gabel, Messer, 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 which is clearly something the neural machine translation system hasn't seen much and is not fluent language in any way, here the neural MT system goes completely off the rails and produces output that has absolutely nothing to do anymore with the input. Suddenly talks about screen monitor styling and projector styling and stuff like that. So we have observed this occasionally in neural MT output. Another piece where work needs to be done is that traditional SMT has a lot of history now of commercial deployment and things like customization and adapting systems to very specific customer needs has been worked on extensively. So for instance, if you have your own terminology saying, yes, I have always translated text, but if you now translate new text, you have to stick to this terminology. We have solutions for that with Statistical MT. Adaptation to customer data, rules for dates units, how to fit that in with this machine learning approach, handling of markup tags, and so on and so on. And generally, these methods do not exist for neural machine translation yet. Other problems is there's no explicit modeling of coverage. So we have an attention mechanism that somewhat tracks the output words that are produced to input words, but it's not as clear-cut that we make sure that every input word is going to be translated. There are research efforts in this direction. There's degraded performance when you go out of domain, and I don't have any hard numbers on that, but there's a general consensus that neural machine translation is actually not that great with rare words. Words that only occur once or twice in the training data. It just doesn't have enough data to learn proper embeddings for them. There are also various deployment challenges for neural machine translation. Speed, especially training speed, takes weeks. Decoding is slower than traditional statistical machine translation. And the only way actually you can train these systems is if you use top-of-the-line graphical processing units, the ones that are used at basically research universities and companies that deploy this, cost about $2,000 each, and also have to be added to any rack-mounted computer you have. Google even has specialized hardware for some of their machine learning neural network efforts. Another big problem is that the process is not very transparent. So when something goes wrong, an output is produced that has nothing to do with the input or is flawed in any other way, it's really hard to then debug this. Arguably, that was already the case with statistical MT, where you at the end had to say, well, the language model liked this word, therefore it was produced. But at least you could still nail it down to very specific numbers in the model, saying, yes, this had a phrase translation probability of 90%, therefore it chose it. Or here was a training example where it got the idea from that this word should be translated that way. So there was still some hope to fix these problems. Now it's much harder when something goes wrong to say, well, one of these million numbers in there is probably wrong, but we don't know which number and what it should be changed to. Another thing I want to say is we're still clearly in the space of data-driven machine translation. So in a way, neural machine translation is still statistical machine translation, meaning that it's still based on statistical evidence of data. So it's not a huge departure, really. It also means for practical deployment, you have the same challenges. So you need translated text to train these systems, ideally in the domain that you care about. Any system you get is only as good as the training data. Data collection and data cleaning is key to have successful systems, and integration into existing statistical machine learning workflows is relatively straightforward because we don't really change all that much, except for these problems with handling complex formatting or markup or specialized terminology, which still need to be sorted out. Okay, and with that, we can move on to the question and answer session.
Thank you, Philip. So we've had a number of questions here during your presentation. So let me just drill straight in and throw the first one at you. So the first question that we had is, how much parallel texts do we need when we use NMT systems compared to traditional SMT? And is it true that NMT systems need more data than SMT systems?
I don't have any hard numbers of that, but that seems to be the consensus in the field, that at least to get going, you need more data. So you can build phrase-based statistical machine translation systems for 1 million words relatively easily, but it doesn't seem to be the case for neural MT, where you just need more data, especially if your data is slightly off domain. Having little data then is really bad. So yes, I can basically confirm that, but I don't have any real hard numbers to point to.
Maybe you mentioned earlier on as well, as a follow-up sort of and a clarification to this question, we talked earlier on about language model for statistical machine translation, the way we use terminology, the way we use TM. Do you mind maybe just spending a couple of seconds to talk about the differences as to the type of data that goes into an NMT system?
Well, yeah, so the NMT system currently are only trained on translated text. For instance, they're not even trained on any additional target language text you can have, which is a huge part of traditional statistical MT. So there's no separate language model really in these models. So there are various hacks around it, how to maybe use additional target language data. It's not quite clear to users. When it then comes to terminology, or do not produce these words, or do produce these words, or whenever this is the input word, that should be the output word, those kind of additional information, it's currently not entirely clear how to integrate that into neural machine translation.
Okay, thank you. So one other question that we had here is, do words have fixed embeddings, and how is the information in the embedding decided on?
So these embeddings are learned with everything else. So I haven't talked about learning at all. I just drew all these big pictures, how everything is connected. But once you draw this picture, how everything is connected, there is a machine learning method called backpropagation training, where you just take this model as it was basically laid out, throw data at it, and just basically then run it for a few weeks, and it learns all the parameters of the model, including the embeddings. So the embeddings are not provided separately. You don't have a fixed embedding for languages that you just build once and then use forever. Whenever you build a neural machine translation system, you also learn these embeddings. You learn all these different parameters that go into that. So the embedding is basically mapping from the one hot vector at the beginning to a word representation in continuous space. So you can look at that as a huge matrix where each row has an entry for a word. These are a bunch of numbers that have to be learned, and they're learned with everything else together.
Okay, thank you. The next question is, typically the input and output of SMT systems are sentences. This limits SMT systems in modeling discourse phenomena. Could we go beyond sentences with NMT systems?
Yeah, there seems to be definitely a straightforward way to do it, because we already have kind of an embedding state that is conditioned on anything previous. So generally, the good news is, yes, it's relatively straightforward to add conditioning context when you make predictions. So going over multiple sentences basically means first read the entire document, distill that information somehow, and then add it as additional input to each prediction you make. And there have been efforts in that area, not that many. I'm aware of a workshop where I partly participated last 2 years ago in the summer, where discourse level neural machine translation was explored. Not to a huge success, but to some degree.
Okay. So for decoding to occur, coding is necessary. But what is the conceptual relationship between coding, decoding, and translation?
So if maybe you should, what we call encoding and decoding. If you look at this picture here, everything above the line is called encoding, and everything below the line is called decoding. So the goal of encoding is to take the input sentence and get a representation of the sentence that is more, some would argue semantic, which captures the meaning of words in context. That's the encoding step. And then taking this encoding of the input sentence, the goal now is to decode that into an output sentence. So that's why this is called the encoder-decoder model also, because we have this very clear encoding step first, and then we have this decoding step afterwards.
Okay, thank you. Next question is, one of the things that's made SMT commercially feasible is adaptivity, to adjust the system's behavior based on small bits of human input without retraining the entire data set, which is too costly. As I understand, that also needed technology innovation. Does currently NMT models have this capability, or is adaptive NMT still some ways off or not feasible with current technology at all?
So the learning algorithm that is used to train all these parameters is called the online learning algorithm, meaning that it learns by continuously processing new training examples. So what that means in practice is that you give it new sentence pairs and it learns from them, and then you give it another sentence pair and it learns from them. So in theory, it should be pretty straightforward to take a model that exists, have some additional training data that might be different in nature, maybe different domain, different style, and then adapt the existing model to that new domain relatively quickly. So there's definitely some hope for that. There's some evidence of this working relatively well. So the standard approach to adapting an existing system to new domain is to just feed in the new sentences you have. How this should work in principle. The question is always, if you give it a new sentence, how much does it overfit to those sentences, and then you can translate just those sentences really well. Theoretically, this could work on a per sentence level, that you have an existing system, new sentence comes in, you adapt it, and now your system knows about the sentence and now can produce better translations. It's still pretty much in the research phase how to actually pull this off efficiently and reliably, that you don't over-adapt or you don't under-adapt.
Okay, thank you. Next question is, a different recent innovation with SMT is interactive translation, when it's not about generating one best translation for the whole utterance, but reaching into the phrase table and pulling out suggestions based on the input sentence, plus what the human translator has entered so far. Do NMT models allow for similar hooks, or are they less transparent black boxes than SMT?
Yeah, so this is actually my hobby topic. So I led a research project called Kasmakat a few years ago, where we explored various ways to do interactive machine translation for statistical models. And obviously, it was then clear that this is something you should also try with neural machine translation. We actually had a paper at a conference 2 months ago in Austin, Texas, at the AMTA conference, the American Machine Translation Association conference, where we had a paper on doing this. So we actually currently, here at Hopkins, a PhD student is working on this, and we're doing user studies with neural interactive machine translation.
So maybe the last part of the question here is, I mean, that you sort of maybe want to spend just 2 more minutes on that, which I think you talked about briefly during the presentation. So one of the questions here was also, the last part of the question is that it was less transparent than SMT. So going back to your presentation, I think you did state quite clearly that with SMT, we got far better understanding of what's actually happening as we go through and we translate. And with the SMT model, we've also got the ability to prune out data if we see bad data that's causing a bad translation. And if I understood you correctly, I mean, you're saying that NMT is a lot more complex, right, even to the point where sometimes we don't even understand why we're seeing particular output, right?
Yeah. Conceptually, if you just look at the models, they're not very complicated, but what's really then going on in the model is really hard to follow. You end up with these 500-dimensional vectors with real numbers, and they produce some other numbers, and none of these things are clear. So theoretically, what happens in neural machine translation or any kind of neural network models is that you have all these nodes in each layer of the neural network, and the idea is that each node learns certain properties of a sentence. Maybe there's a node that is responsible for knowing, oh, there was an opening parenthesis, there should be a closing parenthesis at some point. But which one is doing that and how it is doing that, we just don't even have the right analysis tools for that. So there's clearly some interest to get a bit better sense of visualizing, for instance, at least what is going on there, because it's very hard to track. So even in what I just presented with this attention mechanism, there seemed to be a very clear-cut way to link the output words to the input words, but it doesn't quite work like that either. So it's not necessarily always a reliable indicator of alignment. So yeah, that's a huge problem. It makes it very hard to debug these systems and have good intuitions about how to improve them.
Okay. So before we go to the next question, I just want to, and it seems to be a question that we're getting quite regularly right now, I want to remind everybody that we're always going to put this webinar recording up, and we know there's more questions that we will be able to answer on this webinar. We will put up all questions and answers as part of the frequently asked question after this, a couple of days after this webinar. So if we don't answer your question on this webinar, we will most certainly answer them in the FAQ. Okay, moving on to the next question. You mentioned the importance of the domain a lot, and I was wondering whether register with the dimension that NMT can pick up, or is it more efficient just to pre-process the training data with one domain, identifying examples for formal versus informal register, for instance, and train two NMT systems as if register was in fact a domain?
Yeah. Yeah, so there's this whole space of adapting systems to different dimensions of register, topic. Is it spoken text? Is it written text? Is it formal, informal? Is it chat room? And all these matter a lot for translation. So you could argue that, well, we have the input sentence, so it should be clear from the input sentence which domain or which level of formality it should be in. But that's not always true, because the input sentence might just be too short to give that evidence. If you just take a sentence, a short sentence out of context, it's not quite clear. For instance, if you take the word you in English, should you translate it into du or sie in German, so either as formal or informal text. The sentence by itself might be translated either way. So you need definitely additional information to the input to make decisions about register, as mentioned in the question, or domain in general. And the question is then how to integrate that. So one idea is to just label sentences based on register as formal, informal, or label sentences based on which domain they occur in, and then use that label as additional input, maybe as simple as another input token, to then guide the system, to give the system some chance to hit the right register or the right domain.
Okay.
I would generally say this is still, domain adaptation was never really conclusively solved for statistical MT. There are 10 different methods out there. Nobody really knows what works reliably well. And we are in the very early days on neural machine translation to tackle this problem. It's just a very broad question, because sometimes domains are just really just nuances of each other, and sometimes they're as different as day and night.
All right. So I think we're going to take like another 3 questions before closing, and then I said, I mean, the presentation and the FAQ will be online. So moving on to the next question, output words are predicted from encoding of the full input sentence and all previously produced output words.
Mm-hmm.
Do previously translated phrases, segments in the same project predicting future segments, or is the encoding / context confined to the segment?
So the way I presented it is confined to the segment. As I said, there might be ways to take previous segments as additional conditioning context, but the straightforward system that I presented here, and that is the basis of what currently is the state-of-the-art neural machine translation, what's being used by Google and so on, by us, is only on a sentence level.
Okay. Next question is, by when will NMT commercially deployed on a large scale regarding industries? Will it still be largely based on SMT as a base? I don't know, Philip, maybe you want to give your 2 cents, and then I can maybe add a view to that as well.
Yeah, I think I tried to address that a little bit with my last slide, of saying that it's in a way not a huge departure of what Statistical MT has been doing. It follows the same principles. It fits in the same way into workflows. Now I forgot exactly what the question was. So
yeah, I mean, I guess from my point of view, given what we're doing with customers today, I think it's fair to say that NMT is certainly commercially deployable, but all of the boundary conditions that you've just talked about in your presentation really need to be understood. Mm-hmm. So you need to, on a case-by-case basis, look at the project that you're working on and what the boundary conditions are, and then decide whether SMT or NMT or potentially even a hybrid is the best approach to that particular project. So I think, would you agree that we could say that in principle it is commercially deployable for sure, but not for every single use case?
Yeah, I think that's, I mean, generally you have to fit the technology with the actual customer need and the use case. And there are strengths and weaknesses. I try to go over a little bit what might be possible weaknesses of neural machine translation or possible benefits of neural machine translation. So as was also already asked earlier about how much data do you need. Right. That is a factor that might influence that decision.
Okay. And then last question before we end. Do NMT systems have problems with long sentences, or have more problems with long sentences than SMT systems?
So the one model I first introduced definitely had that problem. I think it's reduced now to some degree in the model that has this attention mechanism. But yes, that is still a concern that longer sentences, since there's not a good way to track coverage, at least the way I presented here, and this is how it's been used, it definitely does better on shorter sentences than longer sentences.
Right, so I mean, I think you talked about both the long sentences being an issue at times, but also what we've also discovered, and you talked about it very briefly, I think is also that it's far more sensitive to domain. So the moment you go out of domain, NMT systems will have very serious problems, and the output will degrade quite drastically. The SMT systems will be that far more graceful.
Yeah, statistical MT and neural MT degrade very differently for domain. So you see in statistical MT, when you give it new domain data, it's very clearly that it's struggling with it, and it just doesn't translate some of the words correctly, or doesn't even translate any of the words because it doesn't know them. And you can see at the output that it's just really bad output. While the neural machine translation system might just say, I can't deal with that input, let's just produce fluent output. And these are the examples I showed earlier, where it just then says, let's just produce something that looks like good English, let's just hope for that, and ignore completely what the input is. So you get very fluent translations, and it's not clear to you that they actually have nothing to do with the input at all, and that's obviously a real problem.
Okay. So I think we're running out of time. in terms of the presentation that we had allotted for this webinar. So I would like to apologize to anybody who put questions in that we didn't answer during this webinar, but again, I'd like to remind you that we will have all of your questions posted as an FAQ together with a recording of this webinar within the next couple of days. I'd also like to remind everybody, as I said, that this webinar was part of a series. So our next webinar that we will send out an announcement on and that you can sign up on our website for, it will then be talking about the practical application of NMT. So we'll follow on from the introduction that we had during this webinar and talk a little bit more about some of the boundary conditions and what that means in real-world applications. Finally, for those of you that are attending TC World in India in February or happen to be attending the Gala conference in Amsterdam in March, Dion Wiggins, our CTO, and myself will be available during those events in person. So if you wish to meet with us and talk about these kind of subjects, then please do send us an email to reception@omniscien.com or sales@omniscien.com, and we would be more than happy to schedule a meeting and talk about these types of subjects in a lot more detail. With that, we're going to end this webinar. So first of all, Philipp, I'd like to thank you for taking the time to present and preparing this presentation, and I'd like to thank all the attendees for spending this time today with us on this webinar, and we look forward to seeing you on one of our future webinars. Thank you very much, and goodbye.
Yeah, thank you for me too.